In this video, we will be discussing why ITRC recommends a bottoms-up approach to characterizing petroleum vapor intrusion sites, one that focuses initially on the vapor source, for example, whether it's LNAPL or dissolved phase, then on the pathway and the effects of biodegradation in the vadose zone, and lastly on the receptor and some of the issues encountered with the sampling of vapors inside buildings and below building foundations. Along the way, we'll try and highlight where PVI characterization overlaps with the characterization of LNAPL and TPH. We'll do this by using an indicator that will appear in the upper right corner of slides where the overlap exists. So let's begin. It's important to start with characterization of the vapor source because the potential for vapor intrusion will vary significantly depending on whether the vapor emanates from an LNAPL source or a dissolved phase source. LNAPL sources will generally represent a greater risk for vapor intrusion than dissolved phase sources because A, LNAPL sources will generate higher source vapor concentrations as a result of direct partitioning of chemicals from the LNAPL to the vapor phase, and B, because LNAPL sources typically generate more upward migration or mass flux of hydrocarbon vapors that occurs because of the source vapor concentrations being higher, but also because LNAPL tends to get distributed above the capillary zone in more permeable regions of the vadose zone. In addition, LNAPL sources will typically contain hundreds of times more source mass than dissolved phase sources, so they'll stick around longer in the subsurface. Lastly, the vapors that emanate from an LNAPL source will tend to biodegrade at slower rates because conditions in the vadose zone near an LNAPL source often become anaerobic or limited by oxygen availability. Rates of anaerobic biodegradation are slow in comparison to rates of aerobic biodegradation for most petroleum hydrocarbons. The net effect of greater hydrocarbon mass flux and lesser biodegradation is that hydrocarbon vapors will tend to migrate farther above an LNAPL source than a dissolved phase source. The PVI risk is also going to be defined by the composition of the LNAPL that resides in the subsurface. In general, the more carbon atoms a hydrocarbon has, the less volatile it'll be, and the more it will tend to absorb to soil. Hydrocarbons with more than 11 carbon atoms are generally classified as being semi-volatile. However, these hydrocarbons generally have lower odor thresholds. As a result, it's the gasolines and jet fuels that represent the greatest risk for vapor intrusion because they're the ones that contain the highest percentage of volatile hydrocarbons. The vapor intrusion risk from diesel and other fuels composed of hydrocarbons with higher carbon numbers, such as fuel oil, will generally occur at sites with shallow LNAPL sources, and these will be sites more prone to odor issues. Understanding the source is particularly important for site screening. As noted previously, hydrocarbon vapors will tend to migrate farther above an LNAPL source than a dissolved phase source. As a result, a greater source building separation distance is needed to screen out a building that's located above an LNAPL source compared to a dissolved phase source. Identifying where LNAPL is present can be tricky, however, especially for residual phase LNAPL, which is not going to appear in monitoring wells. Because of that, residual LNAPL sources are often mistaken for dissolved phase sources, even though they represent a PVI risk that is more similar to the one where LNAPL is mobile or migrating or actually appearing in wells. To help with identifying residual LNAPL sources, ITRC published a table of general LNAPL indicators. These criteria were based largely on assuming that the LNAPL is gasoline. These criteria should thus be applied with caution if assessing other fuel types. The LNAPL indicators are defined based on groundwater and soil concentration data, as well as relative proximity to where the petroleum release initially occurred. The values listed in this table are not intended to be used as absolutes or even in isolation, rather as general rules of thumb and in a multiple lines of evidence fashion. If available, soil gas data can also help in the identification of residual LNAPL sources. Such indicators include oxygen concentrations in soil gas less than 5% by volume, carbon dioxide concentrations in soil gas greater than 15% by volume, and methane concentrations in soil gas greater than 1% by volume. With respect to petroleum hydrocarbons, LNAPL is often present when one encounters benzene, hexane, and TPH aliphatic concentrations greater than the numbers listed. The aliphatics, including hexane, are not typically observed in soil gas above dissolved phase sources because these compounds don't like to dissolve in water or migrate far down gradient from an LNAPL source. Although these indicators do not appear in the PVI tech reg, they were used to help differentiate vapor sources in the development of PVI screening distances. Characteristic relations between concentrations of hydrocarbon, oxygen, and carbon dioxide in soil gas will be discussed in greater detail on the next slide. So after examining the source, it's important to focus next on the pathway, in particular the effectiveness of biodegradation in limiting the migration of hydrocarbons in the vadose. The biodegradation of hydrocarbons will result in the utilization of oxygen and production of carbon dioxide. Oxygen will also be consumed in the oxidation of naturally occurring organic matter in soils and the oxidation of methane that is generated by the anaerobic biodegradation of hydrocarbons both in the vadose and saturated zones. In most cases, the methane generated from anaerobic biodegradation will be completely oxidized to carbon dioxide at some distance above the hydrocarbon vapor source. The point at which this occurs is termed the aerobic-anaerobic interface, and it roughly coincides with the location in the vadose zone where there is A, complete attenuation of petroleum hydrocarbons and methane, B, sharp increases in oxygen concentrations, and C, sharp decreases in carbon dioxide concentrations. The interface is also where temperatures in the vadose zone increase as a result of the biodegradation and oxidation reactions which give off heat. It's also important to point out that the figure shown here is generally a representation of the conditions found in the vadose zone above an LNAPL source, and the conceptual model provides the theory to support soil gas and temperature methods for natural source zone depletion. The aerobic-anaerobic interface would be located much closer to a dissolved phase source, and there would be little, if any, methane generation. The biodegradation of petroleum hydrocarbons will occur in virtually all subsurface environments. It's important then to understand the rate at which biodegradation occurs to understand the PVI risk. Under aerobic condition, the rates are fast, faster for most hydrocarbons than the rates at which the chemicals migrate physically upward by vapor diffusion. How do we know this? Because we typically observe sharp decreases in hydrocarbon vapor concentrations near the aerobic-anaerobic interface. What we see depicted here are the results of published rates of aerobic biodegradation for various hydrocarbons in units of per hour. The rates increase along the x-axis from left to right. N corresponds to the data population used to define the ranges, medians, and means that are shown. These rates are associated with hydrocarbon biodegradation in the aqueous phase, or pore water, which is where most of the microbes are present and where most of the biodegradation occurs in the vadose zone. As indicated, aerobic biodegradation rates are generally higher for alkanes than they are for aromatics such as BTEX and naphthalene. Although the alkanes aerobically biodegrade at relatively faster rates, they also tend to reside or partition to the vapor phase and thus are less available for biodegradation in the vadose zone pore water. When factoring in partitioning, the total effect of aerobic biodegradation on limiting vapor transport is roughly similar for a broad range of hydrocarbons. Unless PVI is likely or suspected because someone is complaining of odors, we choose to focus on the receptor or building last in our characterization because there are many non-PVI sources in indoor air for those same hydrocarbons that are of concern for PVI. The sources include carpets, floor coverings, paints, and numerous consumer products. The chances of detecting these compounds in indoor air is therefore high. The figure on the left shows the results of studies of air quality made inside numerous residential buildings. And as you can see, the probability of detecting BTEX chemicals tops the list, and in indoor air, it's often greater than 85%. For certain chemicals like benzene, there's the added complication that the concentrations in background indoor air can far exceed the screening levels for vapor inhalation, and that's shown in the figure on the right. The other issue we have with measuring chemical concentrations in indoor air is that they can be highly variable in response to air exchange between indoor and outdoor air. The temporal variability that one might encounter is shown here for trichloroethylene, or TCE, where indoor air concentrations varied by over 3 orders of magnitude over the course of a single season. This makes it difficult to know when to collect a representative vapor sample for risk assessment. TCE data are being shown here because such data have not been published for petroleum vapor intrusion sites. In part, this is because cases of actual petroleum vapor intrusion are relatively limited. We also see this variability show up in subsurface vapor concentrations. This slide shows the variability of subslab TCE concentrations below a home over the course of a 6-month time period. At this site, not only did the TCE concentrations vary over time, but the location where the maximum concentrations appeared below the foundation also varied. In general, the variability of subsurface vapor concentrations increases with increasing source separation distance. Airflow is also increased around buildings because of stack or heating effects, wind effects, and the higher permeabilities of the fill material that's often found below building foundations. Again, it can be very difficult to get a representative subsurface vapor sample for risk assessment. Vapors found below a building can also come from indoor air. This figure shows the variability of sulfur hexafluoride concentrations below a home associated with a constant release of sulfur hexafluoride in indoor air. Sulfur hexafluoride is a non-reactive tracer gas that has no known indoor air sources. How does this happen? It happens because buildings can at times be overpressurized with respect to the subsurface when air enters the building at a faster rate than it leaves it. When this happens, the vapors inside the building are forced into the subsurface through the same cracks in the building foundation where they enter during times of vapor intrusion. This all leads us to tailoring PVI investigations such that they focus first on the source, then the pathway, and lastly, the receptor. This is again because A, vapor intrusion will be most affected by vapor transport in the vadose zone, and B, because of all the challenges with sampling for petroleum hydrocarbons within a building and around building foundations. So that concludes this video on vapor intrusion characterization. If you're interested in obtaining additional information on PVI, LNAPL, or TPH, please visit the following ITRC websites, which contain links to both guidance documents and fact sheets, as well as upcoming internet-based training. We hope you enjoyed this video, and thank you for your time today.
The Interstate Technology and Regulatory Council is a nonprofit research program of the Environmental Council of the States. ITRC is a state-led organization composed of over 1,000 members from state agencies, federal government, tribal and international organizations, the private sector, academia, and community stakeholders. Members participate in technical teams which produce guidance, tools, resources, and training materials. If you'd like to be a part of ITRC, please visit the ITRC website at itrcweb.org. You can register for teams and learn more about how you can be an active member. ITRC's usage policy is available on the ITRC website. If you do plan to use ITRC materials, we ask you to review that policy in detail and be sure to credit ITRC. ITRC does not warranty the material nor endorse any specific